All right, so that's what we're going to do. We're going to do 3, 9, 11, 12, 13, and 14. And if we have more time, I'll let you bring up other questions as well. But we'll definitely make sure we get through all of these. So let's start with number 3. I don't know what number 3 is, but we'll see. It says you lift a 25-kilogram child. All right. Slowly carry him 10 meters to the playroom and then finally set him back down. All right. What work do you do when you lift the child? That's just the gravitational potential energy. So this kind of problem is, I'd say we're talking about, kind of multiple choice. You're going to lift the child. Then you're going to carry them sideways there to someplace else. And then you're going to put the child down. So this is the process we're discussing here, right? Lifting and moving the child. Work is done when you lift the child up, sure. You're doing work against gravity. There's no work done by your lifting force when you move them sideways. You're pushing up on the child, but you're moving the child sideways. There might be work done by other forces, a normal force from your body pressing against the child, or friction. Depends on how you hold the child, I guess. But then gravity's doing work bringing them back to the floor. Hopefully, you're lowering the child, so you're doing work too, so that you're not changing the child's kinetic energy. You could just drop the child and let gravity do all the work. They frown on that with the Department of, the departments of stuff. So when we talk about the work being done, it's really just going to be mgh. That's the amount of work being done when you lift the child. There'll be no work done by your forces probably as you move the child horizontally. But when you release the child and they go to the ground, you're probably going to be doing the opposite amount of work and bringing them down. They're losing that much energy. So your numbers are all different. So use your mass and your height, and that's going to give you the right answer. So that was question number 3. And I said, they asked this whole trip, how much work was done during the whole trip. Well, the change in kinetic energy of the child when they make it to the playroom is 0, right? They weren't moving before. They're not moving after. So the net change in kinetic energy is 0. That's the easiest way to determine that this plus this plus this has to all sum to be 0. Does that make sense? All right. Relatively straightforward, but like I said, somebody from first period wanted to see it. So let's go to the next one, which is number 9. Number 9. Yeah, graphs. Okay. It says the top of a descending ski slope is 20 meters higher than the bottom of the slope. A 60-kilogram skier starts from rest and skis straight down to the bottom of the slope. 20% of the gravitational potential energy change of the skier is converted into internal energy. So friction, air resistance. So you got the skier here. And at this point, I'm thinking they have all gravitational potential energy. They're going to ski down to the bottom of the slope. And down at the bottom of the slope, they have no gravitational potential energy. They're at their lowest point, but they probably have kinetic energy. But they just told us that 20% of the energy got left as heat or some other form of energy along the trip. And then you're supposed to look at those idiot graphs and decide which one of those makes the most sense. So let's consider what those graphs are really supposed to be about. So if we consider the fact that there's going to be kinetic, there's going to be gravitational initial, there's going to be spring initial, and then they like to have this work one here, and that has to equal kinetic final, gravitational final, spring final, and any energy added to the environment. So this is their big thing. So what's this going to look like? Well, I don't want to make too much of this because we kind of know, I think, what this is going to look like. at the beginning, there's just going to be gravitational potential, an arbitrary amount. That would all become kinetic, except 20% of it was siphoned off and given to the environment. So 20% is about that much less. So let's say the kinetic at the end is going to be a bar that's shorter than the potential that was there. And the amount of the bar that gets taken away, that has to become the change in internal energy. I'd be looking for a graph that looks like this. So do we have a graph that looks like that? Yes, we do. That's the one I would choose. Questions about that part? Do I think this is going to be on the exam? It could be. There's no reason it couldn't be. Let me go turn those lights out so you guys in the back can see. All right, so is there more to this question or is that it? There's more. Determine the speed of the skier at the bottom of the slope. All right, now we're getting to it. I don't care what the numbers are. You know me. On your test, am I likely to have a numerical test or is it going to be more like an expression test? I think you can expect expression. This problem is so straightforward that it would not surprise me to see this as a multiple choice question. I think it can be done in about a minute and a half. We have MGH at the top of the first hill, and that's going to be equal to kinetic, except that it's not, right? Because 20% of that energy got siphoned off. Now, there's a lot of ways you could write this out. You could write plus, delta U if you want here, and say that delta U is 20% of MGH. That would work just fine, because that's exactly what they said. MGH equals kinetic plus 0.2 times MGH. That's how you're going to do it. You have to take 20% of the gravitational potential energy. A lot of people don't recognize, though, that you're adding it to the side where the kinetic energy is. Or you would have to say, well, if I'm taking 20% away, 80% is left. But that's what really this does, right? If I subtract this from both sides, I will get 0.8 MGH equals kinetic. 80% of the original amount of energy is left over to become kinetic. That makes perfect sense. At least I hope it does. Either way, you set that equal to 1/2 mv squared. Recognize that you do not need the mass of the skier to do this problem and solve for V. Questions? All righty. So next is number 11. And number 11 is, if I remember right, it's the one I think it is. Yeah. We talked about the graph part already. Would you like me to review the graph part? Let me look at the folks at home. Anybody out there want me to review the graph part? All right, so there's a problem with the spring part. At least there's a problem with the way the book presents the spring part. When I say a problem, there's a problem with the way the book presents it compared to the way it will likely be presented on an AP exam. So I want to discuss some of their problems, and I want to discuss how I would modify their problem to be more in line with what I would expect you to be able to do on the test. In doing so, I'm going to be bringing up some stuff that we have not talked about yet that I really think you should know about, meaning I am likely to ask these kinds of questions on your next test. So let's kind of start from the beginning about what this problem is entailing. We've got a block at the top of a ramp, and there's a spring that is in its relaxed condition at the bottom of the ramp. The problem that they have is they're measuring H relative to the absolute bottom, the ground. But they want to know how far the spring is compressed, we don't have enough information to actually get the answer the way they would like it. And part of the reason is, without knowing how far the spring is compressed ahead of time, we don't know where the lowest position of the box is. The lowest position of the box is not the ground. The lowest position is going to be someplace above the ground. So we still have some residual amount of gravitational potential energy. And they don't tell us how long the spring is for us to figure out how much potential energy is still in the box due to gravity when it comes to rest. And that's a real problem, meaning on the actual AP exam, they take that into account. And in this version of the problem on mastering, they just kind of fudge and say that it's small and you don't have to count it. That doesn't really work for us. So I want to describe several things about this problem and several different states of this problem that are within your abilities and some things that aren't, and how I would modify it to put it back within your abilities. First, I have no trouble with starting out saying that this problem begins with a certain amount of gravitational potential energy. The next thing is to talk about the fact that the box is going to slide. And because it's going to slide, it's going to acquire kinetic energy. Assuming for the time being that there's no friction, we are going to reach this point where the box just contacts the spring. It has not begun to compress the spring, but just contacts the spring. At this instant, most of the energy is kinetic, but there's still some gravitational potential because we are above the reference level. So without knowing what the length of the spring is, it's difficult to figure out how fast the box is going just before it hits the spring. But here's the thing. A lot of people think this is when the object's going to be traveling the fastest, because after this, it hits the spring and starts to compress the spring. That is not true. If they ask for what's the fastest the box is going to be traveling, you can't say it's here. And this is subtle, and probably only the super sharp kids here are going to follow this. But when I say subtle, I mean it's worth me asking about in the next test. And that's something that requires us to zoom in here. So let's zoom in and talk just about what happens when the box and the spring begin to interact. When the box first contacts the spring, there is no force yet being applied to the box from the spring. This is Hooke's law, what I just wrote up here. This isn't about energy, this is about force. And Hooke's law states that the force from the spring is proportional to how much the spring has been compressed. But if the spring hasn't been compressed yet, the spring's not pushing on the box. But the box has a force down the ramp from gravity. Right now, this is an unbalanced force. And because it's unbalanced, the box is going to continue to accelerate and get faster. So advance this just a little ways. And let's say that the box has now compressed the spring a little bit. Not enough to stop the box, but a little bit. When the box compresses the spring a little bit, there's still a constant force down the ramp equal to mg sine theta. But now there's a little bit of force up the ramp because we have compressed the spring some. But you'll notice the force is still unbalanced down the ramp. So even though the spring has been compressed some, we now have a little bit of potential energy in the spring, the box is still getting faster. So we're not at our max speed yet, even though the spring is starting to take away some of the energy. We won't be at our maximum speed until these two forces are balanced, because this force is a constant. So the spring has to keep compressing. Eventually, we'll reach a point where we've compressed the spring enough and the net force is 0. That's special. That's when I've actually reached the point where the velocity is max. So that means that's when I have the most kinetic energy. Now, a lot of students won't think of that. The box doesn't stop here, though, because we still have kinetic energy. The box won't stop until we convert that kinetic energy into elastic potential energy. So the box keeps going downwards. The next thing that happens is the spring compresses a little more, and now the force from the spring is unbalanced upwards. Now it begins to slow the box down. So everybody understand this transition part here, that by putting the spring on the ramp, we create the possibility that the maximum speed exists somewhere after the spring is compressed. It doesn't have to be like this. I could have a box that I drop on a spring. The same thing will happen. The maximum speed will not be when I touch the spring, but after I've compressed it a little bit. For the same reason. Because gravity's pulling it down, I have to wait until the net force is 0. I see absolutely no reason I couldn't expect you guys to talk about this. Do the math on it? Maybe not, but talk about it? Most certainly. Now, after this, the box will eventually reach a point where it has stopped. When the box has done that, and it has come to rest, I think we have 2 forms of energy here. Gravitational potential, because we are still above the lowest point. They measure the lowest point here. I'm still above that. But I now also have elastic potential. And this is going to be the 1/2 kx max squared. But there's still a little bit of gravitational potential. We just don't know how much that is. So I've looked at the way they have the problem set up for you guys. It would be very challenging for you guys to get the answer that they get because A, they're making some mistakes here, and B, they don't take into account this extra amount of gravitational potential energy. So in the mastering, I've granted full credit for that. So don't worry too much about getting that answer right if you're worried at all. You guys understand that. I just want to see your work on it. But this conversation, I think this is a conversation I can expect you guys to have. Now, there's an easy way to get rid of this. There's an easy way for a test writer to not create this kind of issue for you. And let me be very honest with you. I would expect my mechanics students to be able to do this problem and have some difficulty. So in AP Physics 1, the way I would modify this question if I wanted to ask it and still get out of you your knowledge of conservation of energy, your understanding of how the spring and how even friction could interact, the easiest way to fix that problem is to just put the spring on level ground after you reach the bottom. Then you don't have any of that problem. I don't have to worry about the maximum speed because I don't have anything pulling down on the box in the direction of the spring. So the maximum speed is everywhere here. I don't have to worry about this issue of having a little bit of gravitational potential energy and elastic potential energy because I am at the baseline when I contact the spring. So that's all you have to do to get rid of that problem that we just discussed. But by having a spring on the incline, they make it a little bit more challenging. Actually, they make it a lot more challenging. So if I was to probably at AP1 level work, I would probably focus something on this. Of course, I also don't have any trouble adding a little bit of friction here. I think that's a more reasonable question for you guys. Makes it less about the math and more about, do you understand energy is being taken out of the system? So I like that. All right. So that's what they gave you. That was what was in the book. This is how I would modify it if I was going to put on the test. Any questions about this?
I was just wondering, why did they, I know you said we shouldn't solve for or like part C, don't worry about it, but why did they include theta? Did that have to do with the sign for part C, like when you're solving for x?
Yeah, because they include theta in their answer because the amount that the spring compresses here, although it might just be x, let's just say it's x, um, that tells us how much the height changed after we contacted the spring. So we'd have to use sine of theta to figure that out. Does that make sense?
Yeah.
Okay. All right. Let's see, what was next? Number 12. All righty. Number 12. Can't remember what number 12 was. I'm sure I've done number 12. What's that? Oh, yeah, number 12. People were asking about this in my research class, and I was mean to them. I'd feel bad about it, but I don't. Let's talk about number 12. They have this has got the bar chart thing too. A lot of bar chart stuff here. I am not particularly happy with their whole premise that I have to consider, like consider just one of the objects and not consider the Earth. I want you to have some, I guess, once you have tried this problem, but I'm really more interested in you understanding how the energy plays a role in this problem. So I know there's graphs there, and I'll get to those answers in a minute. But here's what I expect you to be able to do with a problem like this. So I'm setting the problem up. There we go. This is the beginning state of the problem. I don't think you guys can do problems like this unless you consider what the other states of the problem are. Looking at this isn't enough. I think you need to draw a picture. Now, you guys might not. You guys may be able to do the whole thing in your head. And some of you are probably pretty gifted and very intelligent. But I think it's in your best interest to make something that you can use as a point of comparison. Because although there's not a lot of moving parts here, I do want you to understand that this is just the introduction to this problem. This problem will change for us a little bit next semester when the pulley has inertia. So understanding the moving parts and understanding how they're related, I think is important. I think this is what it's going to look like after it's been released for a few moments. Maybe. Maybe not. Come on, get over there. There we go. There. And I'll have this one way down here. All right. Also, after it's been released for a few minutes, I think that, wait, I think the big one would probably have gone down, not the little one. So apparently, Mr. Shelton, being somewhat of an idiot, kind of messed it up. So let's not tell anybody that I did that. And maybe I do appreciate the fact that nobody said anything. That was awful nice of you. But that's better. The big one goes down and the little one goes up. All right. Yes, that's how life works. I want to put this in here kind of as a baseline for us to be able to know what it is that we're comparing. Because the first thing I need to note is they talk about the fact that this box descended a distance d. So I hope that it's not too hard for you to realize if that box went down a distance d, this box had to go up a distance d. Any question about that? And they're accelerating. So this box now has velocity and it didn't before. But this box has to have the same velocity. Right? They're connected that way. They move the same distance, have the same velocity. So I'm comparing this state, state 1, with this state, state 2. Or if you want, because the way they do the graphs, we could say initial and final. And they have the graph thing with, gravitational initial, and for box 1, gravitational initial for box 2, and all that list. I'm not going to do it like that yet. We can kind of look at those graphs and kind of pull that up, but let's just walk through the problem. And let's compare what box 1 does to what box 2 does. If we believe energy is conserved in this problem, then the energy that is available to the system here has to equal the energy that's in the system here. So what we have to ask is the same questions we've been asking. There's no springs involved, so I think I'm only interested in looking at the gravitational potential and the kinetic at each one of these states. Okay? So we're going to ask ourselves a question. Is the box 1 at its lowest point in the initial stage? If it's at its lowest point in the initial stage, then it does not have gravitational potential energy. It's not above the reference level. Is box 1 moving in the initial state of the problem? If it's not moving, it doesn't have kinetic energy either. So box 1 has no energy initially. Box 2, is it above its lowest point in the initial state of the problem? Box 2 is. Box 2 starts here and ends here. For box 2, its reference level isn't the same as box 1. For box 2, its reference level is here. It's above its lowest point. So it does have gravitational potential energy. In fact, the amount of gravitational potential energy is m2g times d. So it's going to descend a distance d. But it doesn't have any kinetic energy. It's not moving when we first release it. So that's it. This is the entire amount of energy the system has, because it's the only energy it has initially. So that energy is going to get spread out throughout the whole system afterwards. So let's go do this system afterwards, okay? It looks to me like box 1 has been pulled upwards. So work was done on it to increase its gravitational potential energy. In fact, the red line is the reference line for for block 1. The blue line is its maximum height. So it was at its reference level, and now it has gravitational potential energy, m1g times d. But it also has kinetic energy, 1/2 m1v squared. Box 2, it's got no gravitational potential energy. It's at its lowest point. But it has kinetic energy, 1/2 m2v squared. So this is the energy in the final state of the problem. Look at that bar chart. You're going to look for those bars to be in those places. And there's no loss to the environment. The problem is that they asked some questions in a way I was not anticipating when I assigned it. And that is, they asked questions about what would the bar chart look like for just box 1 and the Earth? Or what's the bar chart look like for just box 2 and leaving out the Earth? So some of the charts are a little bit screwy, and I'm not sure I agree with them all. So question 1 is select the correct work energy bar chart for the process, choosing block 1 and the Earth as a system only. Well, block 1 in the Earth, he's got nothing before in the initial state, so it should be empty, but there was work done on that block by block 2. And that's why afterwards it's got gravitational potential energy and it's got kinetic energy. So when you look at the chart, you're only going to have something on the right side that has potential energy and kinetic energy. And they're probably going to fill that work column with some stuff. But I'm not sure I like the way those charts work out. So I want you to be able to do this, what we just put on the board here. That's what I expect you to be able to do. By the way, you don't have to do it this way. You can do this whole problem with net force equals ma. So you don't have to do it like this. You can find the acceleration of the system. You can use the motion equation. It'll work out just the same. I'd be happy to show you that, but I don't think most of you want to see that. All right. I don't know about talking about more about this problem because some of the questions that they ask, I would never ask on the test the way they do it. Like, which one is it? Here, select the correct work energy bar chart for the process choosing block 1, block 2, and the Earth. Well, I'm looking at all their answers here, and none of them look like what I would expect because not one of them shows any potential energy for block 2 before. But block 2 clearly has potential energy before. So I don't know what they're doing with these charts. I want you to have exposure to them, but yeah. All right. There is one on here that I do need to go over. And I don't know what number we just did, but 12. So 13 is the next one. So let's see number 13. Is this the one? Is this the loop-to-loop one? Yeah. 13 and 14. Those are good stuff. I look at number 13 as being like, that could be multiple choice. And 14, probably not. So if you're looking at the level of difficulty of your test, I think 14 would be FRQ. But 13, I could see it being a multiple choice question. And the reason is because this one, you can just memorize this stuff. You should be memorizing the loop stuff. Now, the truth is this problem with the people at the bottom, there's a lot of mistakes that are made here, a lot of simple, stupid mistakes, but you guys have seen your multiple choice. So you understand that it's those little mistakes that always screw you guys over. So let's kind of make sure we don't make those mistakes because I would definitely put this on the multiple choice. The car has kinetic energy at the bottom. And because of that kinetic energy, it's going to have energy at the top. Hopefully it has enough energy to be able to stay in circular motion. That part we don't know, and we won't know until we find out our answer. But at the top, it's going to have kinetic energy and it's going to have gravitational potential. They give us some value for the radius. And they're asking us what is the apparent weight of the person on the ride. So they are asking for the normal force acting on the person from the ride. Now, the normal force is a force problem. To find that answer, I have to remember that net force equals mv squared over r because they're in circular motion. I have to also continue that by saying there's two forces acting on them. There's normal acting downwards and there's weight acting downwards. And we're only interested in the normal force. But they're in the same direction, so I wouldn't subtract them. They're both acting downwards. And more importantly, that equals mv squared over r. This gives me an expression for the normal force, but only if I know the velocity at the top, which I don't have. I have the velocity at the bottom. So you have to know clearly that to get that velocity at the top, you're going to have to use conservation of energy. It's the only way to get the velocity at the top. And we know that 1/2 m velocity at the top squared plus mgh has got to equal 1/2 mass times the velocity at the bottom squared. There's only kinetic energy at the bottom, but we have kinetic and potential at the top. The first mistake you guys are going to make, and I will definitely have a choice where people will put r in for the height. Because you'll do that. You're going to make that mistake. And it's going to make you look like you're not thinking it through. So remember, for any loop problem, your height at the top of the loop is a diameter, not a radius. Don't make that mistake. Or worse, I'm going to give you the diameter and you'll have to remember to cut it in half for the radius. Now, once you have this, you can get an expression for the velocity at the top. You can get a number. And, cancel out the m's, do what you have to do. But when you get that number, recognize that the normal force should be small. Should be smaller than your weight, unless you're going really, really, really fast. We're going to be subtracting it from that mv squared over r. That's it for this problem. We don't have to talk about it much more than that. I mean, if you want, I'll put the numbers in, but my numbers are different than your numbers. So that's all the ones you asked about. Nobody asked about number 14, but number 14 is very similar to this. I was surprised that nobody asked about it, but the only difference here is that in number 14, they're going to launch you into this with a spring. So they want you to die. But they have conditions on the problem. This is more work. I don't think I could do this problem as a multiple choice. I think the amount of time it would take you to do this problem is longer. So this would be more like an FRQ. What I like about this question is you don't have to worry about anything at the bottom except for the spring part. So if you've done question 14, you know that in this problem, they want to know what kind of spring would you have to use so that when you're at the top, you feel 20% of your weight. Now, it's important to note that they are giving you a very important detail by saying that. They're saying that the normal force equals 0.2 times mg. If you can't get that from what they're saying there, you will fail that question. Because that opens up the 0.2 mg plus mg equals mv squared over r. And that begins the problem. This is how you find out how fast you have to be going. And doing this, they do this kind of stuff all the time because your problem ends up being something that only has mg and r in the answer, which is why they like this kind of stuff. For example, this is going to be 1.2 mg equals mv squared over r. So 1.2 mgr equals mv squared. I leave it like this because I know the future of this problem is going to have kinetic energy in it. And kinetic energy is mv squared. So rather than solving this all the way for v, I leave it as mv squared. So that when I say 1/2 kx squared for the spring equals 1/2 mv squared plus mgh for the loop, I have a substitution that's a little bit easier for me to do. Whenever there's centripetal acceleration, you might want to look for that because you have mv squared in both places. It will save you time and probably save you algebra mistakes when you forget to square something or you forget to square root it. But this just means that I get 1/2 times 1.2 mgr plus 2 mgr. Notice the whole right side is all in terms of mg and r. This comes out to be 2.6 mgr. And this side is 1/2 kx squared. You would never make a roller coaster like this. We've talked about that. It's going to snap the necks of all the riders. But the other reason why you wouldn't make a roller coaster like this is, do you notice that in this particular case, you might not notice, I do, m is in our answer. To figure out the kind of spring we would have to use, I would have to know the rider's mass. I mean, how many roller coasters have you gotten on where they put you on a scale first and then put you on the ride? There's very few rides where they ask for your weight. They do exist, but not roller coasters. Generally, the rides where they ask for your weight include you wearing a harness, That's pretty typical. And there's a few water rides where they might ask for your weight. That's because of the buoyancy. They're going to give you a certain raft. But generally, they don't want to ask for your weight. It takes too much time. They want to get 100 people on the ride and 100 people off the ride. They don't want to be stopping everybody and getting their weight. Not to mention, some people are probably a little bit, not interested in telling people their personal information. So, yeah, you would not design a ride like this. Not one that would actually have to measure your weight, at least not directly. You could make one where after everybody gets on, it just measures the new weight of the cars and makes a decision that way. You could, but you wouldn't want to be replacing the spring. You might just try and change how far you pull the cars back. That would be a better way to do that. All right. That's almost all of your homework questions. Are there any residual questions I didn't answer? Test is likely going to be, at the rate we're going, I'm thinking Tuesday. I'm going to put a practice test up online today. I would encourage you to do the practice test over the weekend and bring it to class with you on Monday. The practice test should be 45 minutes of work because it's the length of your test. We'll go over this on Monday. That should give you a good taste for what to expect on your test. The test will be Tuesday. We can grade it Wednesday. And then Thursday and Friday, you have to have your project information in class. I hope that you are doing that. So I've answered a lot of questions about that, both in my research and through Canvas. But hopefully by now you guys have printed out what I've asked you to print out, or at least have found what you're looking for. Please don't forget 18-month calendar. You focus on a lot, but 18-month calendar. If you can't get one, I will provide one, but I'm not going to print 100 18-month calendars if you already use date books that you already have. But I want a physical calendar, something that I can ask you to take out, say, every couple weeks. We're going to be putting a bunch of stuff on it. I want to have that stuff out and available. All right. Well, we should be getting our announcements here any minute. But if there are no questions, that's it for class today. If you guys want to stay to hear what's on lunch or to find out who won the gift card, then of course I would encourage you to hang out for that, because